In this lesson, we're going to continue to look at atmospheric pressure. In the practical demos section on pressure, there's an experiment where I take quite a long tube, about 2 meters in length. I fill it with water, turn it upside down, and then put it in a washing up bowl like this. And perhaps surprisingly, the water stays in the tube. You might expect it to simply just flow out. What's actually holding that water in the tube? Well, in the previous lesson, we learned that there's this thing called atmospheric pressure, which is actually quite strong, and that's pushing down on the surface of the water in this bowl. And we learned that that pressure is approximately 100,000 pascals, which is the equivalent to about 3 large adult elephants pushing down on each square meter of the Earth's surface. So there's quite a big force pushing down on the surface here, holding the water in the tube. If I were to remove this force, for example, take this apparatus and take it to the surface of the moon, where there's no atmosphere at all, then there's no atmospheric pressure, and the water would just rush out of the tube. Okay, so what we'd like to do in this lesson is get a more accurate value for the atmospheric pressure. And so we're going to ask the question, what exactly is the height of the column of water that this atmospheric pressure would support? How big a tube could I use? Well, it turns out that if there's an atmospheric pressure of 1 atmosphere pushing down on the surface of the water in this bowl, then this pressure will support a column of water that's exactly 10.33 meters in height. Okay, so the distance from here to the surface is 10.33 meters. So we should be able to use this information to work out what the value of 1 atmosphere is in pascals, or newtons per meter squared. And we're going to do that by remembering the formula for pressure differences in a fluid. That's to say, we want to calculate the pressure difference between this point and this point. So we need to remember that if we're using water here, that the density of water is equal to 1,000 kilograms per meter cubed. We shouldn't use grams per centimeter cubed here because we mustn't mix the units. We're using height in meters, so the density should be in kilograms per meter cubed. And also we remember that in our calculation we're going to need the acceleration due to gravity, which is equal to 9.8 meters per second squared. Okay, I'm not going to use 10 meters per second squared here as an approximation because we're trying to get a more accurate value for the atmospheric pressure in newtons per meter squared. So we remember that the pressure difference between this point and this point, that's what we're interested in, okay, between this point at the top and the surface of the water here, the pressure difference is density of the fluid times the difference in height multiplied by g, the acceleration due to gravity, which is equal to 1,000 multiplied by 10.33 meters multiplied by 9.8. In fact, I'll put 9.81 there to be really precise, and that gives us a value of 101,300 newtons per meter squared, or equal to 101,300 pascal. So our approximation in the previous lesson, which gave us a value of 100,000 pascal, wasn't in fact a bad approximation at all. So we can say that when the atmospheric pressure is 1 atmosphere a column of water of 10.33 metres will be supported in this tube, which equates to a pressure of 101,300 newtons per metre squared, or 101,300 pascals. So this apparatus that we've got here is something that we could actually use to measure the atmospheric pressure. You're aware that from day to day, due to changes in the climate and the temperature and all that sort of thing, the atmospheric pressure changes. Sometimes it goes up, sometimes it goes down. So we could actually monitor that using this device by measuring how much this column of water were to rise or increase. So what I'm saying is, if the atmospheric pressure one day were to start dropping, then you would notice that as a result the level of this water would also start to drop. That's to say, if the push exerted here becomes less, then the column of water that it can support is lower. If the push becomes higher, let's say if the atmospheric pressure starts to increase, then the level of this water will also increase. The only problem with this device is that it's rather big. You know, it's not easy to get a 10.33 metre tube, anywhere, so it's rather impractical. But there's a much easier way we could do this, and that is to change the fluid that we use in the apparatus. And there's one fluid that is ideal for this purpose because it's a lot heavier than water, and that is mercury. Okay, so the name of this device is called a barometer. It's something that measures atmospheric pressure. So if we change the fluid to mercury, right, then because mercury is a much denser fluid, mercury has a density that's approximately 13.6 times greater than that of water, then the height of a column of mercury that one atmosphere will support will be approximately 13.6 times less. Let's just make a note of that. So the density of mercury is 13,600 kilograms per cubic meter. That's 13.6 times greater than water. Then the height of this column will be 13.6 times less than that of water, and it turns out to be 0.76 meters high, or 760 millimeters. So we say that 1 atmosphere pressure is equivalent to 760 millimeters of mercury. That's what we mean when we say that. It will support a column of mercury that's 760 millimeters tall. Now then, just one more thing I'd like to say about our barometer here and atmospheric pressure, because this sort of question quite often comes up in exams, and you might be asked something like this. What is the difference in pressure, for example, between the bottom of a mountain and the top of a mountain? Okay, like that. Here we've got a kind of flat mountain, and supposing I take my barometer and I measure the pressure here at the bottom of the mountain using this barometer, and then what will happen when I take the barometer up to the top of the mountain? What will happen to the pressure? So really what we're asking is what happens to the atmospheric pressure as we increase in altitude? Well, you've just got to remember what actually produces the atmospheric pressure. Again, from the last lesson, if this is the top of the atmosphere here, okay, then the atmospheric pressure is produced by the height of the column of air above a given unit area. And we said that column has a cross-sectional area of exactly 1 meter squared. And if we do the same thing for the top of the mountain, well, you'll see clearly that the column of air above the top of the mountain is a lot less than at the bottom. That's to say, there's a much smaller mass of air here pushing down on the surface than there is here. So we'd expect the pressure to be less, because the weight of the column of air pushing down is much less at the top of the mountain. And if we take our barometer then in that case and we move up the mountain to the top, then we'll notice that the level of this Mercury will start to drop as we move up the mountain because the atmospheric pressure is decreasing. So we can conclude that the pressure at the top of a mountain is less because the column of air above it is shorter and therefore weighs less.